A commonly occurring problem in a beginning calculus class is you're given a rectangular cardboard with dimensions L and W. And your goal is to cut four congruent squares at the corners. So something like this. So these are squares, which means they all have the same dimension, say x. And then when you remove this, what you get is a piece that looks like this. And then what you do is you fold these flaps along this boundary into the third dimension. So when you fold, what you get is a box that has the same height as x. So from a cardboard, now you have a box whose top is open. It has these four walls that have the height of the height of x. And the question is, what should be the dimension of x so that the volume of this box is maximum? Now, if you cut too small, then your height is going to be too low, and that would affect the volume. Now, if you cut too far away, if you cut bigger squares, then what you're doing is the height is going to be more, but these base dimensions would be small. So there is some sweet spot where when you cut that much square, you're going to have the maximum volume. Now, a lot of times you're given L and W, and you have to come up with X. Now, there is a way you can use calculus. If you're interested, I'm going to describe how you can prove that. But what I want to do is provide you guys with a formula that you can plug and get the answer. So the formula is this. X is equal to, so let's write S minus square root of d square plus p over 6. And let me explain what all of these things mean. S stands for the sum. So S is simply, you're given only length and width, right? So you add them. That's your S. D stands for difference, and L is the one that's bigger minus the smaller, and P stands for the product. So P is product, L times W. Now, this is the formula. If you want to know how you can arrive at that, here's what I'll tell you. So when you remove X, the new dimensions or the dimensions of the open top box are, notice this is going to be L minus 2x and this is going to be W minus 2x. So you multiply those two and also the height, which is x. So when you multiply x times L minus 2x times W minus 2x and expand it, you get a cubic polynomial in x. So that's the volume. To maximize it, you take the derivative, you get a quadratic polynomial, set it equal to 0, use the quadratic formula. And inside the quadratic formula, you do have to do some algebraic trick to come up with something that looks like this. And let me know if you actually found a proof of that, or if you need help, let me know. Thank you.